So, good evening, everyone, and welcome to today's live session for the course Elements of Mechanical Vibration NOC25-ae17. And I'm Rasha Ranjan. I'm an NPTEL PMRF TA, and I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. So, this is the week 3 live session for this course, and we have already completed 2 live sessions in the last 2 weeks. And I hope that the things were clear that we discussed in the live session. So this week's lectures were mostly based on about the damping. So in the last week, we discussed about the viscous damping and we discussed about the structural damping. However, in this week, we discussed about the coulomb damping. So if you remember, coulomb damping was essentially about how friction is going to affect the movement of our system, right? So in the viscous damping, what we were considering that, okay, there is a dashpot and the force which is coming because of that dashpot is of the form C into x dot, where x dot was the velocity. And so that was what we were using, right? But in this case, it is different because in the previous case the force was actually changing with x dot. So if the x dot was changing, it was increasing, force was increasing because it was proportional to x dot. If it was decreasing, the force was decreasing. However, in this case, when we consider the coulomb damping, it is essentially because of friction. And as we know that for the friction, the case is that we have a mass like this, and if we apply a force F, then it is going to apply a friction force over here, which will be equal to mu into n, where n is the normal force. Okay, so this was the concept of, so that was the case of friction. So this was what we considered. Now, depending upon whether the movement is in the forward direction or in the backward direction, the friction force is going to always oppose the motion. That is clear to all of us, right? And the whole equation of motion derivation and how we are going to deal with that kind of a system. It was already done in the lectures, right? I hope that that is clear to every one of you and that doesn't need any kind of further discussion. Okay, so now when we talk about a single degree of freedom system, as the question says, a single degree of freedom consists of a mass of 10 kg and stiffness 3500 Newton per meter. The successive amplitudes after cycles are found to be 80, 75, 70, 67 mm. What is the type of damping, the damping force, and the frequency of oscillation? Okay, so now, firstly, we'll try to analyze how the system is. So it is a spring, then there is a mass, okay, like this, and then here is friction. Okay, for now, we don't know what kind of a damping it is. Okay, so this is our configuration. We have m is equals to 10 kg, and here we have hello, can you please switch off your mic? Thank you. Okay, so this is the case that we have. Now we have the amplitudes, right? After successive cycles. We don't know as of now which kind of a damping is present in the system. So if now I try to plot with the number of cycle how the system is changing, I'll get that if this is the amplitude and this is the time axis, we see the behavior is something like this, right? And then we have 80 mm, 75, 70, 65, and likewise. Okay, and one cycle, two cycle, three cycle, like this. Okay, so intuitively, if you remember when we studied about the structural damping or when we studied about the viscous damping. So if you remember for the viscous damping, the behavior was something like this. But for the viscous damping, the behavior was something like this. But this was not following a linear trend. That this was a curve. If I join all the points of the maximum amplitudes, it was following a curve, right? And we had a relation also on the basis of this, that we had that delta e to the power delta, which was the ratio of xi by xi plus 1, it was constant, right? It was constant for any of the nth or ith cycle, right? But in this case, what is happening? If I look at the ratio, is the ratio same? No, the ratio is not the same. So then what is actually happening? So if I try to visualize how this thing is changing, I see that if I only plot the maximum amplitudes and the time at one cycle, 80, two cycle, 75, third cycle, 70, like this. If you join these points, you're going to get a straight line, right? You're going to get a straight line. And if you remember that for a, I should make it over here also. It will be clear then. Okay, likewise, like this. And this is how it should be joined with the straight line. Okay, so if you remember that this was happening in the case of coulomb damping, right? Coulomb damping where we actually use the effect of friction because of which the system gets damped, right? Now, or it is losing energy. Saying damped is not the correct word. This is essentially losing energy because of that friction, right? Because the system is trying to overcome the friction because of which it is losing energy. Okay. Now, now we know that this is a case of friction damping. But the other question says the damping force. Now, if you remember that there was this whole derivation of the equation of motion and how should we be using it to know that what is the damping force and everything, right? So I'll not get into that. I'll just write the equation. Damping force was nothing but the friction force, which is mu n. N is the normal and mu is the coefficient of friction. Here we are not concerned about the coefficient of friction, so we'll just be evaluating F. If in the question it would have been given that we had to find the coefficient of friction, then we would have used the mass and then gravity and everything to find out the coefficient of friction. So the damping force is this. Now, if you remember that there was a relation, okay, for a behavior like this, Yeah. So if this was x, this value was x, right? Then this amplitude was nothing but minus x plus 2 delta. The delta was mu n by k, or in our case f by k. K is already given in the question. Okay, this was the relation. Also, this was x minus 4 delta. So after every half cycle, the amplitude was getting reduced by what? Twice of delta amount, where delta is F by K, frictional force divided by the stiffness. And after every one cycle, the total change in the amplitude is 4 delta, which is 4 frictional force divided by K. Okay. So we know that after one cycle, the amplitude x after one cycle is x at 0 minus 4 f by k, right? This is a relation that we get. This is for a complete cycle. For a half cycle, it would be 2f by k. Okay. So this is what we get. Now, the question is that if this is x0, this is x1, then we can simply put it in this equation. We get 4 f by k is equals to x naught minus x1, which is nothing but 5 mm. So this much meter. So from this, if we evaluate f, it is nothing but 5 by 1000 into k, which is 3500 divided by 4, right? This will come out to be, this is gone, and we have 835 by 8, 4.375 Newton. Let me check. Yeah, 4.375 Newton. So this is the value of what? This is the value of the damping force. F is the damping force, which is nothing but the frictional force. Clear? The third part of the question says frequency of oscillations. Okay, so if you remember, while we were studying this graph, we also got to know that unlike the viscous damping case, where the time period of oscillation was actually the damped natural frequency, right? There was a relation to find out the damped natural frequency, which was dependent upon the natural frequency and the damping ratio. In this case, that is not the same. In this case, the system is going to oscillate with the natural frequency itself. Okay, there is no concept of damped natural frequency or anything. It will oscillate at the natural frequency only. Okay, so if we find out the natural frequency of the system, that is going to be the frequency of oscillation. So this was omega n. Okay, so if you remember, maybe I should use another slide. So if you remember that the natural frequency of any system was under root of k by m, right? Because we would change the equation of mx double dot plus kx is equals to 0 to the form x double dot plus k by mx is equals to 0, and this was essentially omega n square. So we already have the value of k, which is 3500, and we have mass 10 kgs. Under root of 350, I've already calculated the value, 18 radians per second. Okay, so this is going to be the natural frequency of the system, which will also be equal to the frequency of oscillation as for coulomb omega is equals to omega n. Okay, so this was the question. The main thing which I wanted to convey in with this question was that if we have the amplitude, maximum amplitudes, or either we have some kind of a time response of the system. Okay, and we don't know that whether my system is undergoing viscous damping or it is going frictional damping, or if I have a system wherein I don't know what kind of a damping is present in there, and if I sorry, give it an oscillation, give it an initial condition, it is going to oscillate and come back to a point. So how will I know that whether I should model it as a viscous damped system, or whether I should model it as a structurally damped system, or as a this one, frictional damped, right? So, but if I get the time response, and if this behavior is a curve or if it is a straight line, I would know that how should I model my damping. Okay, so through this we can actually create the model in our mind, and then we can work on it from the experimental values. Other than that, if we have the time response, we can simply conclude which kind of a damping it is. Okay, now coming on to question number 2, which says that for a metal block attached to a spring of stiffness K is given an initial displacement 10 centimeter from its equilibrium point. After 2 seconds, it completes 5 cycle of oscillation and the final position is 1 centimeter from equilibrium position. Find the coefficient of friction between the surface and the block. Okay. In the previous question, we just had to find out the damping force, right? So we were not concerned about the coefficient of friction or the normal anything. But in this question, it is specifically asked that we have to find out the coefficient of friction, right? So how we are going to deal with this? Okay, this is our system. There's a metal block of mass m and it is attached to the rigid this reference with a spring of stiffness K. Okay. Now it is given an initial displacement of 10 centimeter from the equilibrium point. So from its equilibrium point means that it is at this state. There is no force acting and there is no elongation or compression of the spring. It is like this. It can be considered that this may be considered as a vertical spring mass system. It is applicable for that also. In that case, equilibrium point means that there is a balance of mg and kx. Okay. Now, initial displacement of 10 centimeters. So let us say this is our equilibrium point. And then the initial condition is 10 centimeter. 10 centimeter from the equilibrium state. Right? Now it is saying that it completes 5 oscillations. Means after 5 oscillation, it is somewhere here at 1 centimeter. After 5 oscillations, right? So it started from here. The block was here at t is equals to 0. And now it is here at t is equals to 2 seconds. Okay. Now we have to find the coefficient of friction. So since it is the case of Coulomb damping, we know that after every cycle there is a decrement of after every cycle there is a decrement of 4 mu n by k. Decrement cycle comma this is decreased from the initial amplitude. Right. Now we have 5 complete cycles, right? So if x, which is the initial displacement, it was 10 centimeter, and then after 5 cycles, means 5 times of this value, 4 mu n by k, right? So after 5 cycle, the decrement is, okay, I should first write it like this, 5 times 4 mu n by k, right? So x minus 20 mu n by k is equals to what? X at 5. And x at 5 is nothing but 1 centimeter. Right? So, okay. So, now what will I do? I will just put up the values, right? And I'll convert it into meters. So, 10 centimeter, which is 0 point minus 20 mu n by k is nothing but 0 0.01. This implies 20 mu n by k is 0 0.09, which means now this n is nothing but mg, right? So I can replace it over here. I have 20 mu mg by k is equal to 0 0.09. But the big question is, I have the value of g, 9.81 meter per second square. But what about the value of m and k? There is no mention of the values of m and k in the question, right? So how will I evaluate this? So see, there is a very important thing written in the question which says that after 2 seconds, it completes 5 cycles, right? Now you see this mentioning of 2 seconds is going to help us out with the values of m and k. How? Because if a system is completing 5 cycles in 2 seconds, then it is completing one cycle in how many seconds? 2 by 5. And the time taken by the system to complete one cycle is a time period. And we can use the time period to find out what? The frequency, the natural frequency. Correct. And the natural frequency is related to the m and k. So we have time taken to complete 5 cycles is 2 seconds. So time taken to complete one cycle is 2 by 5 seconds. right? And this is our time period. And we know that the time period is related to omega as 2 pi by omega is equals to time period, which implies omega is 2 pi by the time period, which is 2 pi by 0.4, and this will give us the value. I have evaluated it somewhere. Omega, yeah, it is 15.708 radians per second. Okay. Also, for Coulomb damping, omega is equals to omega n, which is nothing but under root of k by m. And over here, as you can see, we have 20 mu mg, 20 mu mg by k is 0.09, right? And we have over here this. So if we replace this by omega n, we get 20 mu into 9.81 divided by omega n square is equals to 0.09, and this value is 15.708 whole square. So now if I put up all the values for mu, I get 20 into 9.81. So after doing all the calculation, you can get the final value. I've written it, the final value. It turns out to be 0.1132. So this is the value of the coefficient of friction between the surface and the mass, right? So I hope this is clear how we are doing it. It is simply the concept of Coulomb damping. Okay. Now coming on to question number 3. It says that a spring of stiffness 10,000 Newton per meter is used to suspend a mass of 20 kg. S is missing over here. A Coulomb friction of magnitude 50 Newton is subjected in vertical motion. Okay. Find the number of half cycles elapsed. So first we'll just make the system. So we have a mass suspended like this. Okay. We have the stiffness K as 10,000 Newton per meter, and we have the mass M 20 kgs. Okay. And because of this surface, which is here with the mass in the vertical direction, there is a friction that acts. Here it will not be equal to actually mu n, it will be equal to some friction F. Okay, this is just a model. Okay, there is no F which I have shown N that is actually I'm applying in the system, but it would have been because of the physical nature of the system, that there is some kind of normal force that is acting, because of which the surface is applying a friction, right? Now we have to find out, okay, if value is also given 50 Newton, okay, number of half cycles elapsed before it comes to rest. Okay, initial, okay, yeah, it is given in the end if the mass is initially displaced by 5 centimeter. So we have x as 5 centimeter, which is the initial displacement. Now coming on to calculating the number of half cycles. Firstly, what is the half cycle? So If you remember, there was a plot like this. So this was a complete cycle, and this is what we call as half cycle. Okay, and for every half cycle, there is a reduction of how much? If this is x, this is minus x plus 2 mu n by k, or in this case, we already have the value of mu into n, which is f. Okay. So after every half cycle, the reduction is 2f by k, right? So I have to find out the value of number of half cycles it takes to come to rest. The first question is, when is it going to come to rest? See, for a spring mass dashpot system, when we consider a viscous damping, it will come to rest when there is some equilibrium condition that reaches and all the transient is damped out, right? But this is not the case because there the damping force was C into x dot, and it was acting in the direction where opposite direction to the stretch, like in the direction of the inertia only it was acting. Here that is not the case. Here the friction is acting in the opposite direction to wherever the motion is happening. And secondly, we know by the concept of friction, the body is only going to move if the applied force is greater than the value of the frictional force, right? Now there is again concept of static friction and kinetic friction. We are not going over there. It is very simple that if there is a mass m and then there is a force F, so mass is going to move only and only if F is greater than equal to mu mg. For any value of F which is less than this mu mg, frictional force, the mass is not going to move. We are applying the force, but the mass is not moving. We have no work done. Okay. So in this case also, the same thing is going to happen. Though my mass must have not come to an equilibrium position, but because of this friction, whatever the force that my mass is having because of the spring stiffness, right? Because of the spring, see, the spring is going to, if it is not coming back to the equilibrium position, the spring is always going to apply the force. But if for that force my mass is not moving, why is it happening? Because the spring is trying to move my mass in a particular direction and the friction is relucting it. And when this frictional force is actually higher or equivalent to the force which is applied by the spring, because of the stiffness of the spring, the mass is not going to move, though it is not at the equilibrium position. Okay, so because of that, what is going to happen? Kx, where x is at some rth cycle, half cycle. So Kx at r is what? It is less than or equal to the frictional force, which is F, right? So Xr is less than or equal to F by K. Now what is Xr? If you remember, Xr was nothing but initial displacement minus. For every half cycle, we have a reduction of 2F by K. And likewise, there are R half cycles. So this will be into R. Okay, so we have XR, sorry, this one, X minus twice of R F by K is less than equal to F by K. Okay, I hope it is clear. So we have to find out the number of half cycles, which is easy. We have the value of X, 0.05 minus R into 2 into 50 divided by K, which is 10,000. It's less than equal to F50 divided by, okay. So this will come out to be, take two zeros. So we have 0.05 minus 0.005 is less than equal to 0.01 R. So we have R is greater than equal to 0.045 divided by 0.01. This implies R is greater than equal to 4.5. Okay, but then again, the number of half cycle should be an integral value. So we say that, okay, maybe I should consider another slide. So we will write that the system will come to rest after 5 half cycles. Okay, so this is the answer for part A. Now part B. Part B says that the time taken to come to rest. Okay, we evaluated in the A part the number of half cycles. Here we have to evaluate the time. Okay, so for one cycle, see again, omega will be equal to omega n, because this is a case of Coulomb damping and the system is going to oscillate at the natural frequency only. So if I evaluate omega n, I can get time period, and if I get time period, I can use the number of half cycles to relate my time period into total time, right? So if there are 5 half cycles, so there are how many full cycles? 5 by 2 full cycles. Okay, so for one cycle, the time taken is tau, then for 2.5 full cycle, the time taken is nothing but 2.5 tau. Okay, so this is what it is going to be. Now for omega n, we need to use under root k by m, which is 10,000 by 20, which is under root of 500, and it will give us the value. Okay, I've not written that value, but you can just calculate. We can for now take it as this. So time period is going to be nothing but 2 pi by omega n, just 2 pi by under root of 500, and this will turn out to be 0.2810 seconds. Okay, so the total time is going to be 0.2810 into 2.5, and this will turn out to be 0.7025 seconds. Okay, so this is going to be the total time taken for this is taken by the system to come to rest. Okay, Now the third part, if the final spring extension, okay. So the final spring extension we have to calculate. For that, again, we are going to use the formula x minus r into 2 f by k at any rth at any rth half cycle. Okay, here the number of half cycles were 5. So x of 5 is going to be x minus, we have 5 into 2 into 50 divided by 10,000, right? Anyways, for 4.5 and above, this is going to be what? If you see it clearly, it should be 4.5 over here. And if I use 4.5 over here, I'm going to get what? I'm going to get x5 is equals to 0, right? It will be 0, right? It should be 5 over here. Yeah. It will be what? Is equal to 0. We calculated over here, r should be greater than equal to 4.5, right? And when we use that formula over here, what do we get? Now this will multiply with this will take two zeros with itself, so it will turn out to be 0.05 minus 0.05, which is going to be equal to 0. So in this case, the final displacement after it is coming to rest is 0. But is it the final value that we have to report? Because if we look at the question very clearly, it is asking about the final spring extension. First thing, in question number 2, it was specifically mentioned. See, look over here. Initial displacement of 10 centimeter from its equilibrium point. But in this question, there is no specific mention of this thing. It is just written that the mass is initially displaced by 5 centimeter, which means that this does not consider the effect of equilibrium position. It is actually the total displacement, but not only the, it is the total displacement, but not the, please switch off your mic, Mr. Pradeep Kumar. So here, hello. Yeah, okay, fine, thank you. So over here, there is no specific no specific mention about that the displacement is done with respect to the equilibrium point. Okay, so it means that the displacement is given considering the equilibrium point. It means it is from the zero reference where there is no deflection of the spring, right? So if the question is asking that we have to find the final spring extension, though my system has come to zero value with respect to what? With respect to the coulomb damping, but still it is going to show some displacement. Why? Because we have a mass and we have a spring which is in the gravity, right? So there is some deflection of the mass which is because of balancing its weight. So by that we get delta as nothing but mg by k, and this turns out to be, we have m as 20 kgs, 20 into 9.81 divided by this, and this will give us a value of 0.01962 meters. Okay, so the total final spring extension is nothing but x of 5 plus 0.01962. Okay, this should be delta. So this is the final answer for the part C. Okay, I hope this is clear. This was a very easy question. All right, coming on to question number 4. Okay, so the question number 4 says that for a 1 degree of freedom system that consists of a mass, spring, and damper. Okay, the damper consists of both the viscous and coulomb damping that acts simultaneously. Okay, which means that there are both the components C x dot, and along with that there is friction also. Okay, so free vibration reduces by 1% per cycle when the initial amplitude is 20 mm and reduces by 2% per cycle when initial amplitude is 10 mm. So we have to find out the value of F by K for Coulomb damping, where K is the stiffness definitely and F is the friction force. Now see, we have okay, there is both Coulomb and viscous. Okay, so whatever be the decrement or whatever be the oscillation of the system, how is it actually happening? So we know that for Coulomb damping, the behavior was something like this. And for viscous damping, we had so if I connect all these dots, so this was viscous, this was Coulomb, right? Okay, so we had a relation for the viscous damping, which was we had logarithmic decrement delta as ln of xi by xi plus 1, and this was equal to e to the power 2 pi eta, where eta was the damping ratio. Well, for the Coulomb damping, we had a relation x of I plus 1 is equals to xi minus 4f by k. Right? This was the relation that we had, if you remember. Now, if I want to use these relations to get what I want, first thing is that there is reduction, right? Now, the reduction in total is 1%. There is some contribution of viscous damping and there is some contribution of Coulomb damping. I don't know what is the amount of contribution, but I do know that how can I relate my initial state to the state after one cycle by these two relations. And anyways, whatever is going to be the total change, it is going to be the sum of these two changes, right? It is going to be the sum of these two changes. It's very simple. So for the viscous damping case, if I say the change percent is going to be what? It's going to be 100 into initial state, so xn minus after one cycle xn plus 1 whole divided by xn, right? This will turn out to be 100 into 1 minus xn plus 1 by xn. Okay. Now I do have a relation for this. I have xi by xi plus 1. So if we do its inverse, we can get this relation. So this will turn out to be 100 into 1 minus e to the power 2 pi eta. Right? This is the change of percent because of the viscous damping. So we'll just write it as x, not x. Yeah, x will work. Delta x because of v. Okay. And now if I consider for the Coulomb damping, I have delta x c change percent right. Here what relation do I have? Here I have the relation xn minus xn plus 1, right? I do have the relation for this. This will turn out to be what? We'll have xn over here and we are going to have 4 f by k into 100, right? This is what we are going to get. So here I have written one thing wrong. Here it should be I and here should be I plus 1, right? Then we are going to get this relation. Now, at any point of time, the total reduction percentage is going to be what? It is going to be nothing but 100, 1 minus, sorry, e to the power 2 pi eta plus 400 f by k. And here there will be an x. This is the total reduction because of both the viscous and Coulomb damping. Now x I have already been given in the question for two cases, like for x 20 mm, the reduction is 1%, and for x 10 mm, the reduction is 2%. Okay. So now when I put it in the this equation, what do I get? I get 100, 1 minus 2 pi eta plus 400 f by 0.002. Okay, it should not be 20 mm, it should be 20 centimeters. Centimeters. Yeah, then it will be 0.02. Okay, 400 f by this into k is equals to 1. And then we have 100, 1 minus e to the power 2 pi eta plus 400 f 0.01 K is equals to 2. These are the two equations, right? And now we can use it to find whatever we want. See, what is interesting is that for the viscous case, the decrement, if you see, it is irrespective of the initial state, right? It is irrespective of the initial state. While in this case, it depends on the initial state, right? So now if I take this as equation 1 and this as equation 2, and I subtract equation 2 from equation 1. Subtract equation 1 from equation 2, what do I get? I get 400 F by K into 100, which is, sorry, I'll just write it like this, is equals to 1, right? From this I get 400 F by K is 100 minus 50 is equal to 1, right? Now, F by K is nothing but 1 by 400 into 50, which turns out to be 5 into 10 to the power minus 5 meters, right? So this is what we are going to get from over here. You see, using this equation that we got over here, you can actually evaluate their specific contribution or how much it has decreased because of viscous damping and how much it has decreased because of coulomb damping. But this case, which we have used for solving this system, is applicable for a linear range. And if we consider that both are independent of each other. While in physical case, that doesn't happen. These are actually dependent on each other. But for now, we have just taken this for the simplicity of solving this equation and using the concept that both, if we consider both the friction as well as the coulomb, how do we deal with the system? Okay. So I hope that this is clear. Now, coming on to question number 5. So question number 5 says a spring mass system of mass 5 kg, an impulse of force 500 Newton is applied for 0.1 second. This results in an oscillation of amplitude 0.25 meters. What is the natural frequency of the system in hertz? Okay, firstly, for a mass spring mass system, 5 kg, K is not given. Okay. An impulse of force 5 Newton is applied for 0.1 second. So the impulse F time t is applied such that okay. So this is the impulse. Now we have that it results in an oscillation amplitude of 0.25 m. Firstly, if you remember that for an impulse, we have F dt, which is equals to nothing but mass into velocity, momentum, right? Initially, it is in a static state, the equilibrium state, x is 0, velocity is 0. After the impulse, we consider the x still as 0 because it occurs for a very small time. And the velocity can be evaluated from this equation, which is because of the momentum that it gets because of the impulse. So over here we consider, here we have V naught. The V naught we can get from over here, right? So we have V as F dt by m, which is nothing but equal to x naught dot, the initial condition. See, if you remember that when we were solving the case of a spring mass system, undamped spring mass system, we evaluated the analytical solution by first derive the equation of motion, and from that we derive the analytical solution. So the analytical solution was assumed of the form cos of omega t minus phi, where x was under root of x naught square plus v naught by omega n square, and phi was tan inverse v naught by x naught omega n, right? So if we use this in this equation, what are we going to get? Our x is equal to 0. So if x is equal to 0, this is going to be what? This is going to be infinity, and phi we are going to get as pi by 2. Okay. And for this, we have this as 0. So our x is nothing but v naught by omega n. The solution x of t can be written as cos of omega t minus pi by 2. Then we have cos of pi by 2 minus theta as sine theta, and cos of minus theta as theta. So using these both relations, we get sine of omega t. V naught by omega n sine of omega t. And V naught is what? X naught dot, which can be written from this equation as f of dt by m omega n sine of omega t, right? So in the question, it is already given that an oscillation of amplitude 0.25. We know the oscillation amplitude as 0.25. So I'll just maybe write over here. This is the general solution for an undamped spring mass system. Okay, this is the amplitude and this is the phase angle. Okay. Now using that, we know that x is equals to 0.25, which is nothing but f dt by m omega n. So if we put the values, f is 500, dt is 0.1, m is 5, and omega n we have to evaluate is x 0.25. So omega n, this is the equation that we get. Now upon solving this equation, we get the value of omega n as 40 radians per second. 25, if I remove this, I get 100. Remove this, I get a 10. Is this gone? 5, 2, 25, 20, 40 radians per second. Okay, but I think in the question it is given that we have to evaluate the natural frequency of the system in hertz. So we have a very simple relation. Omega n is equals to 2 pi f, where omega n is in radians per second and f is in hertz, which is 1 by time. So f is omega n by 2 pi, which turns out to be 40 divided by 2 pi This gives a value of 6.366 hertz. So this is the final solution. This was for a very simple case of impulse where you had to find out only the amplitude. This further things of this convolution and everything, I think it will be discussed in next week. But for now, for solving the assignment problem, this much knowledge is enough. Okay. Coming on to question number 6. A dam system has a damping ratio of 0.02 and natural frequency of 100 Hz. Then half power frequency bandwidth is. See, firstly, we have a system. A spring mass dashboard system. M, C, K. Okay. Now for this system, if I add a forcing, F, right, what is going to be its equation of motion? Its equation of motion is going to be mx double dot plus cx dot plus kx is equals to F, is equals to F. Now if F is periodic, it is going to be cos of omega t. I'm not getting into much derivation of this because we will do this in the coming week. But for now, I'll just write the equation. So if the solution is assumed to be x of t as x cos of omega t minus phi, then in this case, x is f divided by k minus m omega square whole square plus c square omega square to the power 1 by 2. And then we have phi as tan inverse of c omega by k minus m omega square. This equation you are going to get in any of the vibration book, SS Rao or anything. Okay. Now, for this, if we try to take k out in the equation of capital X, and then we have f by k. So we define f by k as static deflection delta st. Okay, so in terms of this, then we can write the equation x by delta st as 1 by 1 minus omega by omega n square plus 2 eta omega by omega n square to the power 1 by 2 to the power 1 by 2. Okay, and then yeah, then we say that x by delta st can be written as m, where m is nothing but the magnification factor. Okay, now for this, if omega is equal to omega n, if I take omega as equal to omega n, what is going to happen? I'm going to get x by delta st as what? If I put as omega by omega is equals to omega n, the first term will get 0 and the second one will have only 2 eta and square and 1 by 2, it will get cancelled, so I get 1 by 2 eta, 1 by 2 eta. So from this relation we say that for small eta, the maximum value of this magnification factor occurs when omega is equal to omega n at the natural frequency, which turns out to be nothing but 1 by 2 eta, which turns out to be 1 by 2 eta. So this 1 by 2 eta is written as Q and is known as quality factor or Q factor. So now if you have the damping ratio for a system and you need to find out its quality factor, you can simply evaluate by using 1 by 2 eta. Second thing that over here they are asking is that half power frequency bandwidth. So see what happens is that if I look at a plot, the plot is somewhat like this, right? With this value is Q. So if I evaluate the value over here, Q by under root of 2, corresponding to that, I'm going to get two values over here, which are R1 and R2. So this R1 and R2 are the half power points. They are known as the half power points. Okay. And if I want to find out the values of this R1 and R2 corresponding to when Q is Q by under root 2, what do? I have the equation of transmissibility ratio, right? Wherein I'll put what? 1 by 2 under root 2 eta. Okay, so I get 1 by, for now we assume R is equals to omega by omega n for the simplicity of writing. It's under root of 1 minus R square whole square plus 2 eta R whole square is equals to 1 by 2 under root 2 eta. Squaring off on both sides, we get 8 eta is equals to 1 minus R square whole square plus 4 eta R square. Okay, so from here we get 8 eta square should be there is equals to 1 plus R square minus 2 R square r to the power 4 plus 4 eta R square. So final equation r to the power 4 minus 2 minus 4 eta R square plus 1 minus 8 eta is equals to 0. Now if I solve this equation and I find out the roots of R, that is going to be the values of R1 and R2. That is going to be the values of R1 and R2. So if you remember that for an equation of the form ax square plus bx plus c is equals to 0, the roots are given as minus b plus minus under root b square minus 4ac divided by 2a. So using this, we can write r square is equals to 1 minus 2 eta square okay, here should be an eta square, right? Yeah, 1 minus 2 eta square plus minus 2 eta into 1 plus eta square. Now if we consider that the eta is very small, if eta is very small, then r1 comma 2 square is going to be what? 1 plus minus 2 eta, right? 1 plus minus 2 eta, because if I'm considering eta as small, this I'll assume as 1, this I'll assume as 1, so it will be just 1 plus minus 2 eta. Okay, so this is what we get. Now, so omega 2 square minus omega 1 square, what I can write it as? I can write it as omega 2 plus omega 1 into omega 2 minus omega 1, right? This will turn out as what? This will turn out as, since if you see, we have omega 2 square minus omega 1 square, okay? And we know that r is nothing but omega 1 comma 2 divided by omega n. So we can write it in terms of r as omega n into r. So we have r1 and r2 square. So we can write omega 2 square minus omega 1 square as what? We can write it as 1 plus 2 eta square minus 1 minus 2 eta square into omega n square. Now using the binomial expansion, since eta is very small, we can write it as 4 eta omega n square, nearly equal to, right? Further, as we know, omega 2 plus omega 1 is equals to nothing but twice of omega n. So twice of omega n into omega 2 minus omega 1 is equal to 4 eta omega n square. We can cut this and we get omega 2 minus omega 1 as 2 eta omega n. Or we get 1 by 2 eta as omega n divided by omega 2 minus omega 1, and 1 by 2 eta was what? Our quality factor. So what do we get? We get Q is omega n divided by what? Omega 2 minus omega 1, which is the thing that is asked in our question, which is the half power frequency bandwidth, delta W. Delta W is the half frequency, half power frequency bandwidth. Half power frequency bandwidth. So now if I have the value of quality factor and the natural frequency, I can find this half power frequency bandwidth. Or if I have the value of power frequency bandwidth and the natural frequency, I can find out the value of quality factor. Okay. So as given in the question, we have the damping ratio as 0.02 and natural frequency as 100 Hertz. It has 0.02 and omega n is 100 Hertz, which 100 Hertz into 2 pi. And I have to evaluate, I have to find out the value of half power frequency bandwidth, which is going to be delta W is going to be what? Omega n into 2 eta, which is going to be 2 pi into 100 into 0.02. This will turn out to be 25.1327. So this everything will be discussed in the coming week. This I have discussed over here because you people have questions related to this. So this will be helpful in order to finding out that how you should be solving that question. Okay. So coming on to question number 7, we have for the ratio of omega by omega n, will a single degree of freedom system will attain minimum amplitude under harmonic forcing. There will be no will firstly over here. Secondly, the question is asking about it will attain minimum amplitude under harmonic forcing. So this is something which is related to the previous question. So if you remember in the previous question, we found out the value or the relation of phi like this, right? We found out the relation of phi like this, which was phi was tan inverse C omega by K minus M omega square. So if we change it into the form of R and eta, we can write it as tan inverse of 2 eta R by 1 minus R square. This is phi. Okay. So now it is asking us about the amplitude. The amplitude was what? Whole square plus 2 eta omega by omega n whole square total under root. We have to find out the minimum amplitude. Now see, this x by delta st is what? It is the ratio of the amplitude divided by the static deflection. So static deflection is not going to change. What is going to change? X. X will depend upon what? Omega and eta. Omega and the natural frequency of the system is not going to change. Only omega and eta values are going to change. So if we look at this very clearly, and if we take the values such that omega by omega n is equals to 1 by under root 2, right? What are we going to get? See, you're going to get the value as 1 by the omega by omega n is what? 1 by under root of 2. So if we'll do the square, we are going to get 0.5, 0.5 whole square. Over here also, if we do omega by omega n, we are going to get 1 by under root 2, right? And we are going to do the whole square, right? But the question is that when are we going to get the minimum amplitude? Now see, over here, in order to get the minimum amplitude, the thing which is under the root, it should be what? It should be maximum, right? It should be maximum. We know what is going to be the maximum value. It is for the case when omega by omega n is equals to 1, which is the case of resonance. Okay. But if we take omega by omega n is 1 by under root 2, it is going to give us the minimum value. Okay. Coming on to question number 8. We have an engine that drives a generator through a gearbox system. The speed reduction is changed from 5:1 to 2:1. Then what is the percentage change in the equivalent inertia of the engine? See, we have an engine that goes like this. Then we have gear system over here. This is the generator. Okay. Now, if you remember that this was discussed in the class as well, that for this kind of a system, we actually transfer the system in such a way that we can model it something like this, that the engine and generator are actually mounted on the same shaft. the engine and generator are actually mounted on the same shaft, and for that we evaluate I or J equivalent for the engine. J equivalent for the engine. See, though this, if you consider this engine and generator, it is actually a 2 degree of freedom system. If you remember when we discussed the concept of degrees of freedom, we discussed that a system can be a 2 degree of freedom system. I can see it as a 2 degree of freedom system, but actually I can convert it into a 1 degree of freedom system if those 2 degrees of freedom, those two movements, I can find a relation in between them such that one will become dependent on the other. Okay. Like for example, we discussed about the case of a simple pendulum where the pendulum was actually oscillating in the x and y plane, right? But it was considered as a single degree of freedom. Why? Because we had a relation that the bob, which was connecting through the thread or a rod, and the length of the rod or the thread, it was not changing with time. So we had the relation that x square plus y square is equals to L square by the right angle triangle. Now for every x, I can evaluate y by that relation. So technically, I can convert it into a 1 degree of freedom system. Okay. Similarly, if we consider this, we have an engine, we have a generator. They both are having their own movements, right? But because of this gear by which they are connected, there are two gears that are connected to the engine and then to the generator, and then they are meshed. Because of this, I can find a relation between the engine movement and the generator movement. Okay, because of that relation, what I can do is I can make my system as a 1 degree of freedom system because I can write the movement of engine with respect to the generator. And that way I can make my system 1 degree of freedom system and then I can deal with that in that way. Now, for that, I need to find out I equivalent, J equivalent, sorry, not I, it should be J because it's a torsional case and we consider the polar moment of inertia over here. See, initially, if my engine was, let us say, moving with omega E and generator was omega G, okay, and JE, JG. Now I need to model my engine and I need to find out J equivalent such that the energy that it is giving or the energy it has, it should be the same as the earlier. Earlier as in when it was JE, the energy should be equivalent to when it is J equivalent. So let the current energy be half JE, let's write it like JE equivalent into omega. We are modeling it in terms of the generator, right? So if the generator is having an angular velocity of omega g, the engine should also now have a velocity of omega g. So it should be omega g square is equals to half je, and here we'll have omega e square. This relation I can use to find J equivalent. So by this relation, J equivalent E is nothing but JE omega E square by omega G square. Now if we look on the question, it is written that the speed reduction is changed. So let us say that the, for now, speed reduction is n is to 1. Now what does this mean? See, I have an engine which is driving, okay, and that driving engine is actually giving power to the generator. Now the engine, if it is oscillating as omega E and the generator is not oscillating, actually it is rotating. Engine is rotating as omega E and the generator is rotating as omega G, then there is a relation because of this speed reduction. The speed is being reduced. So the speed reduction is such that omega E by omega G is equals to n by 1 is equals to n by 1, or omega E is equals to n times of omega G. If I put it in this equation, what do I get? I get Je into n square omega G square by omega G square, which is equals to n square Je. Okay. For n is equals to 5 is to 1, or n is to 1 is equals to 5 is to 1, we have J EQE 1 as 25 into Je. 25 into Je. And for n is to 1 is equals to 3 is to 1, J equivalent of engine 2 is equals to 9 Je. So these are the two equivalent moment of inertias. Now the question asks that what is the percentage change in the equivalent inertia of the engine? Okay. So by this it means that if the reduction is done from 5 is to 1, okay, is it 3 is to 1 or 2 is to 1? Okay, it is 2 is to 1. Sorry. 2, 4. So if the reduction is done from 5 is to 1 to 2 is to 1, the system changes from 25 is to 25 Je to 4 Je. Now if you want to find out the percentage change, it should be defined as percentage change in moment of inertia of engine with speed reduction is equals to JEQ E1 minus JEQ E2 divided by JEQ1 E into 100. This turns out to be 25 Je minus 4 Je divided by 25 Je into 100, which is equals to 21 by 25 into 100, 84% reduction. So you look over here, my system is exactly the same. There is no change of any kind of a mass or any kind of a design of the system. The mass is same, design is same, everything is same. Only the reduction is happening. Okay, the speed reduction is reduced from 5 is to 1 to 2 is to 1. Now because of that, there is 84% reduction in the equivalent moment of inertia of the engine. 84%, which is a very large amount, right? So this is what happens. What did we do? The engine is the same, the generator is the same, but the only difference is that now because of the reduction ratio, the equivalent effect has been reduced by 84%. Okay, I hope this is clear. Now coming on to the last question. See, over here we have an IC engine drives a generator through a 4 is to 1 speed reducer. Okay, the engine is directly coupled to pinion of the gearbox as shown. The mass moment of inertia of the engine moving parts is 0.9 kg meter square. Of the engine, we have the mass moment of inertia J of engine as 0.9 kg meter square, and that of the generator rotor is 5.4 kg meter square. This is 5.4 kg meter square. The generator shaft is 2 centimeter diameter and 0.5 mm length. The shear modulus of the shaft material is 90. gigapascal. Determine the non-zero torsional natural frequency of the system in radians per second. Assume the gears to be rigid and massless. The first question is determine the non-zero torsional natural frequency. Non-zero torsional natural frequency means that the system is not behaving like a rigid body. If you remember, for this system, what we were doing, we were converting it into of this form, something like this. We were converting it. Okay. For this, if there is any relative motion in between them, then only it is going to show us any torsional natural frequency. Like for the two systems, if there is any relative motion, then only it is going to have a non-zero torsional natural frequency. Otherwise, it is going to have a zero frequency. Reason being that it will behave like a rigid body. If there is no relative motion in between these two, engine and generator, there then it is going to behave like a rigid body and it will have the zero natural frequency. Not zero, actually it will be the first frequency is going to be zero. Clear? So we are concerned about the relative motion to be precise, right? So the question is that what do we do? First thing first, we have the speed reducer 4:1 and we have the engine's moment of inertia. We need to first convert it in terms of the equivalent moment of inertia. So J E equivalent is going to be what? If you remember from the previous one, we had JE into omega G by omega, sorry, it should be omega E by omega G square. Omega E is by omega G is what? It is 4:1. So JE into 16, which is 0.9 into 16, and it will give us 14.4 kg meter square. Okay, done. Second is, now we know the generator's moment of inertia and we know the equivalent moment of inertia for the engine. Second thing about finding out is the stiffness. See, first thing, the engine shaft is very small. It is almost very close to the gear. So we can neglect as of that, and that is what is not given in the question also. But for the generator shaft, it is 2 centimeter in diameter and 0.5 meter length. So we don't need to calculate its stiffness. Okay, so stiffness is going to be what? If you remember the torsional stiffness for a spring, torsional spring, if you model a shaft as a torsional spring, it was J by L. Okay, here this J is of the shaft. J is of the shaft. So Js is what? Pi by 32 d to the power 4. Pi by 32, 0.02 to the power 4, and this will give us the value of 1.5708 10 to the power minus 8 meter to the power 4. So K is going to be G, which is, let me check, G is 90 gigapascal, 90 into 10 to the power 9 into 1.5708 10 to the power minus 8 divided by L, which is 0.5 meters. So when we do all the calculation, this K value turns out to be 2827.43 Newton meter per radians. Now I have the value of K. I have the value of K, and this is going to be the effective stiffness itself. But I do need a value of I equivalent to be precise, in order to find out the natural frequency, right? So when I have to find out that, what do I have to do? Firstly, we need to find out that what is the relation of I equivalent in terms of I, not equivalent actually, it should be I effective. Equivalent is for the engine. So I effective, how do we actually calculate it? So as I told that the non-zero frequency is going to come only when there is a relative motion between the engine and the generator, right? So let us say that the relative motion phi is equals to theta 1 minus theta 2. Okay. Also, since the system should have a balanced moment, it should be like I1 into theta 1 plus I2 into theta 2 should be equal to 0. This implies theta 2 is equals to I1 theta 1 by I2. So if I write the total kinetic energy, it will be what? Half I1 theta 1 dot square plus half I2 theta 2 dot square. Now what I can do, I can use this relation and replace theta 2 by theta 1. So I'll get half I1 theta 1 dot square plus half I2 half I2 into I1 by I2 theta 1 dot square. Okay. So this will turn out to be what? Yeah, okay, fine. This will turn out to be what? Half I1 theta 1 dot square plus half I2 and 1 I2 will get cancelled. So we'll have I1 square theta 1 dot square divided by I2. Okay, this I can write as half theta 1 dot square into I1 plus I1 square by I2. Okay, this is clear. Now, we assumed phi was theta 1 minus theta 2. So in that case, phi dot is what? Theta 1 dot minus theta 2 dot. This is easy. Okay. Okay, maybe I should write a line over here that the non-zero, again I would like to mention over here that in the question it is specifically asking the non-zero torsional natural frequency. So the non-zero torsional natural frequency will exist if there is a relative motion between the object. Otherwise, the system will behave like a the system will behave like a rigid body. Okay, it is very important. That is why we are considering this uh, relative motion phi as theta 1 minus theta 2. Okay, I hope this is clear. Again, if we use the relation theta 1 dot, sorry, theta 2 dot, which was equal to I1 theta 1 dot by I2. I1 theta 1 dot by I2. What are we going to get? Phi dot is equals to phi dot is equals to, okay, there should be a minus over here, right? A minus. Anyways, it will not cause any difference in this derivation because there is square, so minus will get cancelled, but it will definitely affect over here. Phi dot is equals to theta 1 dot. Phi dot is equals to theta 1 dot plus I1 by I2 theta 1 dot plus I1 by I2 theta 1 dot. So from here we get phi dot is equals to theta 1 dot into I2 plus I1 by I2. This implies theta 1 dot is nothing but I2 phi dot divided by I2 plus I1. Okay. Now if we use these equations, let us name as 1 and this as 2. So using 2 in 1 gives kinetic energy as half I1 plus I1 plus I1 square by I2 into theta 1 dot, which was I2, into phi divided by I1 plus I2 whole square. Whole square. This will turn out to be half I1 I2 plus I1 square by I2 into I2 square by I1 plus I2 square phi dot square. This will be half I2 and I2 will get cancelled. If I take I1 as common, I1 plus I2 into I1 divided by I1 plus I2 square into phi dot square. Now this will get cancelled with this and turns out to be half. Okay, sorry. Here will be one I1, but here will be one I2 as well. Yeah. Half I1 I2 by I1 plus I2 phi dot square. This is the kinetic energy. Now if I relate it with what? Half I effective I dot square. What did I get? I get I effective as I1 I2 divided by I1 plus I2. If we look closely, it is something related to when two springs are in series. The effective stiffness is of this form. So we can write it as 1 by I1 plus 1 by I2. 1 by I1 plus 1 by I2. So the effective inertia is 1 by J EQ of engine plus 1 by J of the generator, right? And as I obtained 1 by J EQ of engine, it was it was 14.4 plus 1 by 5.4. Yeah. So this is going to be the I effective. Okay. Uh, and K effective. So basically omega n is going to be under root of K effective by J effective or I effective, anything would work. But over here we have calculated K for the generator, and for the your engine we have not evaluated it. So for that, because the stiffness related to the shaft connected to the engine is neglected, as it is very small as compared to the generators, and that is the reason even its values are not even mentioned in the question. Okay, so kg is essentially equal to K effective over here. Kg is only equal to K effective over here in this question. Okay, so now if we evaluate the value of natural frequency, it will turn out to be, firstly evaluating this, it will get us a value of 0.2546 kg meter square, and for omega n we have K effective, which was 2827.43, 2827.43 divided by, this was a Newton meter, and this was 0.2546 kg meter square under root. So if you'll evaluate this, I've already done the calculation. It will turn out to be 26.8303, 28 point, oh sorry, 26.8303 radians per second. This is going to be the one non-zero torsional natural frequency. This is going to be the non-zero non-zero torsional natural frequency of the system that is given in the question. Okay, so I hope this was clear to everyone, and even if there is any question, you can go through the lecture and then ask me in the now also or in the next live session. So I have tried covering all the questions in such a way such that it will be helpful for you to tackle the assignment problems. If you'll go through the lectures and if you'll go through this live session, it will be easy for you to tackle the questions, okay? And the questions are easy, and it will be easy for you to actually evaluate. Only you have to be very alert while attempting the questions. You have to read the questions very properly, as you have seen in this live session also, one or two questions where we saw that the information is given in the question, but how do we have to interpret it is very important. Like for the question where it was given that this number of cycles it was completing in this number of time, but there was no mention of mass and stiffness. So we use that concept to actually replace the value of k by m under root of k by m by k from that natural frequency. So that is how you need to attempt the questions. You need to be very alert and you need to know some basic relations like omega is equals to under root k by m. Then we have the relation of k effective and j effective. Then likewise, you need to remember these relations. However, if you'll keep solving the questions from book or for the assignment problems and everything, you'll by time you'll just remember it. Don't need to memorize it like yeah, like you just keep sitting and memorizing. You should not do that. You should just keep solving the questions, and yeah, that will be helpful for you. So that is it for today's live session, and we'll meet next week, Tuesday again at 6 p.m. Okay, so thank you so much.